bandwidth concerns. Okay, it's 11 a.m. Eastern, 5 p.m. Central European Time. Greetings to everyone for Ocean Exchange. First, I want to recognize our sponsors, and you see them on the slide here. There are others, and you can go to oceanexchange.org. We could not do this without them, and we're very grateful to them. We have quite a mix of people today. Because we have some university innovators, we have quite a group of people with .edu email addresses. So I welcome all of you. And our theme today is about university-based innovation. So let me tell you about Ocean Exchange. We are a nonprofit and we exist for one purpose, and that's to help advance the adoption of innovative solutions from startups. Those startups can be garage engineers, they can be out of universities, they can be out of big research centers, national labs. We are agnostic about the form of solutions, but we do focus on healthy oceans, healthy and resilient coastal systems, and we have some particular interest in sustainable ocean shipping because of Wallenius Wilhelmsen. You see them mentioned here. We give away 2 $100,000 non-dilutive grants. Non-dilutive means it's free money. We don't take equity for that. And if you're a student, that's a term you ought to get to know because it's important. Free money is important. We also have a $10,000 award that's just for undergraduate and graduate students. And we'll have these awards in 2021. Get to know us and understand that process. Contact me. I'd like to get to know any of you, whether you're on the corporate side or NGO side or university side. We are recording this session and it will be available in a link a little bit later. So our twist today is about university innovation, and we have 2 academics who have some success actually, and they're going to talk about that. But what's really interesting to me today is that both of them are working in solutions that relate in the field of chemistry, biochemistry, but chemistry. We often talk to people at the university level and ask them to help us access innovators in their system. And some of them say, oh, but my university doesn't have an oceanography program. My university doesn't have a marine science program. And I'm going to tell you, and then there are a couple of people here today that are going to try to convince you that ocean-based innovation can come out of almost any discipline. And you're going to hear about some chemistry disciplines today. Chemistry innovations. So with this, I'm going to turn it over to Dane Dunstan. He is our MC and he's going to lead you through our program. We're going to take questions at the end. Dane will facilitate that. And Dane, it's yours now.
Thanks, Millie. All right, everybody, welcome. Excited to be here. Let's go to the next slide, Alice. Just a couple of things to think about. For Q&A, please feel free to put any questions into the Q&A box. You'll find a link to it or a button for it at the bottom of your screen. Do that rather than the chat, and then I'll moderate the questions there. Sometimes questions come in that 2 or 3 people might ask a similar question, so sometimes I'll put those together. And we're going to have fun. Really got an interesting program today. You know, sometimes over the years with Ocean Exchange, there's so many different kinds of programs. Some are very scientifically simple to understand. Somebody's got something to deliver very clean water to the poorest people in the world. That's pretty simple to understand. A couple of years ago, we had a winner that had a very simple way to lift drag nets off the bottom of the ocean so shrimp fishers wouldn't mess up and get all this bycatch. You look at that, it's very easy to understand. Today, we're going to look at some things about which I can tell you I have no clue. Chemistry in high school was not my best subject, but what is interesting and easy to understand is there is something in our world right now that wants to happen. And that is making better use of our resources. And it's interesting to be in a time like we're in, where we've got all the things that are going on in our world. Um, Very often, it's times like that that the greatest innovations appear. And they seem to appear in clusters, and they seem to appear with a lot of people getting involved. Case in point, 1937. In 1937, something really interesting happened. Researchers all over the world started to make really fast progress in the development of computational engines. Computational engines had been around for about 100 years at that point. Uh, we're talking about math that would take people at a desk with a pen or an adding machine maybe a year to solve a problem. People said, look, we need to be able to solve these problems faster. One of the reasons they did that, they were all hearing the drums of war, and knowing that things were coming, they understood that innovation and radical computational logic was going to be very necessary to study weather patterns, navigation, encryption, ballistics. So all over the United States and all over Europe, people in universities were looking at how to use new technologies like vacuum tubes to really get fast action in computations, and to do math that would have taken somebody a week to do, and to do that in a few seconds, what we now call a computer. And what grew out of that was a partnership between universities and governments, particularly in the United States and Britain, on ways to solve problems. And in a very, very real sense, and most people don't think of this, World War II was largely won with better data. The ability to really do serious science really helped win that war. So fast forward 20 years to 1957, and Sputnik launches the space war. The Russians put up the first satellite that orbits the Earth. The United States starts to respond, and that response came from a variety of different places. But what was driving it was a sudden view that we needed a way to take all these great computers now that had come out of World War II and that had been developed in the 50s, to be able to start linking them together so scientists could work together and share data. It started primarily in universities or corporate labs in the US and Britain. Universities wanted to share research and data. Corporations who were working on government contracts and defense contractors wanted to be part of that, but they also saw a commercial usage for computers that could be worked together. And then the military needed them for the space race and for defense, and to have a distributed computer network that would survive an attack during a nuclear war or other kinds of disasters. That led to something that we now call the internet. But it was taking research out of the labs, putting it into action in the real world through businesses and public and private partnerships. So what we're going to be talking today is that there's work that's happening all over the country. I will tell you, just this summer, I've seen an acceleration of requests from people watching the fires in Australia at the beginning of the year, in California towards the end of the year, all the things that are going on with storms and the number of hurricanes we've had, where people are saying, oh, whoops, this climate change thing is accelerating. What can we do to accelerate our work on sustainable technologies in universities, get public-private partnerships to get these scenarios out into the world, and close the gap between science and business and getting solutions into place in our world. So that's what we're going to talk about today. And we've got some really, really great minds with us today. If we go to the next slide, Alice, Dr. John Wensveen is a real great person to be talking about this, because he's not an academic. He's somebody who's, although he has a doctorate, he spent most of his career actually in business, putting it into place, putting solutions into place. So, John, why don't you talk to us about the state of play of getting public-private partnerships to get research out into the real world?
All right, thank you, Dan. I appreciate that. Alice, if we could just go to the next slide, please. And just one more if we could. Thank you, appreciate that. Well, good morning, and thank you for the opportunity to participate in today's Ocean Exchange event. I'm going to talk to you about innovation over the next approximate 7 minutes. And what's really great about today's presentation is that the timing of today's webcast, which is focused on university-based innovation, could not be more timely as the world around us evolves quickly as a result of natural forces and unnatural forces, of which the current pandemic is a good example. Academic institutions, public and private, across the nation and throughout the world are being forced to be more innovative and entrepreneurial than ever before. The strategies needed to survive and thrive are different today than they were 5, 10, 15, and even 20 years ago. Academic institutions must think more like businesses and work toward self-sustaining models, and they must do so in partnership with the external community. By external community, I'm referring to industry, government, and the community at large. Also, if we could go to the next slide, please. We're in an age of global acceleration and global disruption, and this is not a trend that will ever disappear. They'll just take on different life forms. There's a large and growing gap between academia and industry, and this is a concern on a global scale. In order to close the gap, there is a need to establish what I call co-invested partnerships between all levels of academia, including K through 12 and higher education and industry. Universities have historically been at the forefront of research, and yet much of this research has not been tied into the innovation ecosystem, meaning much of this great work is not commercialized. If you go to the next slide, Alice. Before we get too deep into today's discussion, it is important to define what innovation means so there is a common understanding. Unfortunately, the word innovation is frequently used very loosely and therefore is sometimes lost in the mix. Innovation is about addressing a challenge that results in a solution and in many cases can be commercialized. Innovation might result in a new method, an idea, or a product as examples. Innovation must add value. Innovation is about ideas, creativity, collaboration, and commercialization. There are literally hundreds of definitions for innovation, but all lead to one common accepted phrase: fresh thinking that creates value. I love the word ecosystem, and in my own world, this is something I am engaged with every day. Innovation cannot be successful without an innovation ecosystem. An innovation ecosystem includes intermediary and integrative organizations that are surrounded by 7 key elements, which include research universities, entrepreneurs, investment capital, workforce, social and professional networks, business environment, and quality of life. Most communities lack 2 of these key elements, which include workforce, i.e., a talent pool with the credentials to support emerging industries, and investment capital, and the example there is access to angel investor and venture capital networks. University-based innovation must be closely aligned with local, regional, national, and international trends, challenges, opportunities, and strategies. Lack of this awareness will most likely lead to failure. If we could go to the next slide, please, Alice. One of the fast-moving trends for universities has resulted in the establishment of what I'm calling innovation centers, or more commonly known as entrepreneurship centers, depending on where you are in the world, where ideas can flow in different ways. Such centers often have a diverse range of external partners, and this is where the conversation related to co-invested that I mentioned earlier comes in. Innovation centers are typically focused on incubation and/or acceleration, and this is great, and there are many examples of success. However, there's more to innovation than incubation and acceleration, and many models do not support the full life cycle of the founder's journey or the researcher's journey. The next evolution of the innovation ecosystem will focus on increased public-private partnership models that better link all stakeholders. In the case of the university, this means great linkage to the internal environment, including administration, faculty, staff, students, and alumni to a certain degree. Also, in the case of the university, this means the establishment of co-invested long-term partnerships with the external community at large, primarily focused on industry, government, and funding sources. To use a marriage analogy, the time for dating and long engagements is over, and partners must get married and collaborate as one to achieve success. In many cases, the future innovation ecosystem will be driven by innovative universities and colleges, for that matter, that set up a private partnership model with the public. So a P3, as they're most commonly referred to as, that is truly co-invested, acting as the gateway or portal to the internal and external networks. The resulting innovation center model breaks down siloed environments and is not owned by a college, department, or even a discipline. Instead, it is an unbiased asset acting as a collision station whereby opportunity and resources meet and great things happen. Go to the next slide, please. The Future Innovation Center will focus on key themes like innovation, technology, and entrepreneurship, and truly forward-thinking models will support the innovation lifecycle around 4 pillars, which include ideate, incubate, accelerate, and post-accelerate. Success will be measured on clearly defined outcomes that might include examples like breakthrough ideation, the creation of new technologies, a talent skills pipeline that provides relevant credentials, new jobs, company formation, and the scaling of early stage and young startup companies. Innovation centers are economic development engines for communities, and in addition to what I just presented in terms of defined outcomes, innovation ecosystems are great tools for recruiting new enterprise from other communities, which also includes importing new talent as well as increased access to funding opportunities. Successful models provide customized programs, events, and a comprehensive list of wraparound services meeting the needs of all stakeholders. The challenge when we talk about the future is that the future is already here, and we must ask ourselves, what are we doing about it? Truly successful innovation centers will not try to serve all, but focus on what are termed defined targeted industries, also considered the high-wage, high-growth sectors or verticals. In the case of Broward County, where I reside, which is the greater Fort Lauderdale area, we have 7 defined industries, and our evolving innovation model is focused on aviation and aerospace, global logistics, headquarters, life sciences, which includes medical and health, manufacturing, marine industries, and technology as examples. Next slide, please. As I begin to wrap up, it is important to note the importance of fostering an innovation mindset within the university structure and in the community at large. This is easily said, but often challenging to implement successfully, and this is why higher education institutions are revisiting their operating models. The next 5 years will result in a facelift in terms of how universities focus on innovation and how communities play a key role in this. I cannot underestimate the importance of creating co-invested partnerships between academia and industry. Universities, if they are open and flexible to doing things differently, compared to the historical models that most are familiar with, will play a key role as a change maker in the innovation ecosystem. The world's most innovative universities will focus on subject matter that advances the world, invents new technologies, and power new markets and industries by establishing a centralized go-to resources that houses all of the resources and wraparound services that are required for success, which includes physical and virtual access. And if you go to the final slide, please. In conclusion, the time to innovate is now. And I'd really like to thank you for listening to my presentation. And now I'd like to turn it over to the next part of the program. Thank you.
Hey, John, thank you very much and would you stay around because we're going to talk to Tom and Amy, and then I want you back to help us have a discussion about
Absolutely.
where we're going. So
Yes,
next slide, I want to introduce Dr. Tom Manning. Tom is a professor of chemistry at Valdosta State University, and his work is really focused on pharmaceutical agents coming out of largely out of the ocean. And Tom, I'm not going to say anything more. Let me just hand over to you and tell us what you're working on.
All right. Well, thank you very much. My name is Tom Manning, and I do a lot of work with biofilms in the ocean. I should point out, I'm not going to talk about it today, but we've done a fair amount of work with oyster and coral restoration. You might say, what does that have to do with biofilms? Well, for larvae of either species to settle on a surface, it has to have a chemically and biologically friendly environment to go to. And we try to do that using green technology and with economical materials. But I'm going to talk about drugs today, and particularly one. Next slide, please. Okay, so what I'm going to talk about is a drug called bryostatin that comes out of the ocean. It's a kind of a landmark drug for marine natural products. And I'll point out that right now in the state of Florida, there are 800,000 people that have Alzheimer's disease in different stages, right? It's a worldwide problem. There's no cure for it. There are only drugs that treat different symptoms of the disease. There is a drug called Briostatin that has entered preclinical trials, human trials. It's gone through phase 2 that has some hope of actually reversing the disease if given in the earlier stages. The problem with it is it costs right now approximately $18 million per gram. It's extracted from a marine organism, obscure marine organism called Bugula arantina. The first time it was identified was in the Florida Panhandle back in the 1960s, but it takes 14 tons of this small obscure creature to get a half an ounce of the drug on a good day. I will point out that there have been other times when tons of this creature have been dragged out of the ocean and they got no bryostatin out of them. So what we do, what our focus is we chemically recreate Bugula, we put it back in the ocean and try to grow the bacteria. I should point out that marine bacteria are notoriously very difficult to grow or impossible to grow in a lab. There's been a lot of attempts at moving genes around to get them to grow in others, more common bacteria. That has failed. There has been organic synthesis. Some of the elite groups have published some very elegant, very nice synthesis, but they economically don't work for producing enough for a world supply. So you can see their eggshells, right? Bugula's outer covering is limestone impregnated with iron. So what we did was a chemical analysis, both organic and inorganic, and then we try to replicate it. So for example, we'll take eggshells, impregnate it with some inorganics like iron, magnesium, zinc, and then some organic nutrients. And then we place it in the ocean. We let the bacteria grow out and we bring it back to the lab and we extract it. That sounds pretty simple, right? And the process is pretty simple, but it took us years and years to get there because we had to get the mixture right, the nutrients right. We had to get the organic nutrients right. The location is critical. We can go 50 feet away and not get any bryostatin from our yields. And then even how we do the extraction is different than how people used to do extractions from Bugula and arantina. So it hits the points of being a green technology. It's economical. You can do it on a large scale. What I should point out also is that we're doing this for bryostatin. We've done it for another drug called ET743. We've looked at some others. But we're doing this first as a method of synthesis for known marine natural products to make it much cheaper, but also as a discovery method. So rather than having to go around and look for different marine creatures that might be defending themselves with drugs, that's chemical defense, we can put this out and see what's there. We can change the matrix, we can change the nutrients, we can change the location slightly, and we'll get different bacteria. I should point out that there are billions of species of marine bacteria in the ocean. It's completely, almost unexplored area. And it's going to be something that's very fruitful for years, for probably centuries to come. So it is a green technology. So if there's any questions, I'd be happy to answer them or hand it off to the next speaker.
We'll take the questions in a little while, Tom. It's really fascinating. I'm going to have some questions for you myself. And Millie wanted everybody to know that we know you because you have been a faculty advisor to two of our Ocean Exchange collegiate finalists, and they were great programs. And so I want people to know this is not just like some lab that's doing research. This is teaching. This is the students learning to be scientists and really start to make changes in the world. It's really great stuff. So Tom, hang on. We're going to talk to Amy next. Alice, we can go to the next slide. Dr. Amy Wright is with Florida Atlantic University's Harbor Branch Oceanographic Institute, and her research is vast, but also a lot of it focused on what we can pull from the oceans to cure some pretty tough diseases. So Amy, let me hand off to you and then we'll all have a conversation.
Okay, so the next slide, please. So our program focuses on finding these small molecules found in nature that might have utility in the treatment of diseases. And can you hear me?
Yes.
Okay. And anyways, so that's what we are focusing on. And wherever you have biological diversity, you have the opportunity to find chemical diversity. And about 50% of all small molecule drugs that are currently used clinically have their origins in compounds that are found in nature. And so we're looking to find new ones like that. So next slide, please. So at Harbor Branch, we've been extremely fortunate that we had the Johnson Sea-Link submersibles, which allowed us to dive to 3,000 feet of depth and to selectively collect and environmentally correctly collect different organisms that we can use in our studies. Currently, we work with NOAA to use remotely operated vehicles to go down and collect these unusual organisms. I have partners in my lab who, Peter McCarthy, who isolates microbes from these organisms, much like we heard Dr. Manning. Next slide, please. So I just wanted to talk about a success and then a forward-looking little story. So the first one on the left-hand side of the screen, that complicated structure is called ET743 or actinicidin 743, and Dr. Manning mentioned it earlier. And it comes from a little tunicate that you can find all throughout Florida. And the original work to discover that there was anti-tumor properties from this tunicate actually happened at University of Miami way back in 1967. My small role on this was to help determine the structure of this molecule. It's fairly complex and it has like a propeller-like shape that allows it to selectively bind certain sequences of DNA and modify what's happening in tumor cells. It also has some immune properties, and immune suppressive and immune modifying things are very important in cancer treatment these days. So now I'm going to switch to the other side of the screen where I want to make the point that where we have new technologies, we can find new discoveries. And this is work that I'm doing in collaboration with Dr. Esther Guzman, who is our very talented cancer biologist at Harbor Branch. And one of the new technologies that we have access to is called a high content imager. And a high content imager is kind of a super microscope that can very, very rapidly gain very detailed images of cells. But not only can it do that, you can stain them with various fluorescent probes and measure the levels of various proteins or the number of cells, et cetera. It's a really amazing new tool. And what it allowed Dr. Guzman to do was to grow cancer cells in 3D spheroids. And so if you look at the left-hand screen, you see this kind of blue blob. And what you might be able to see is that each of those little blue dots is actually the nucleus of a cell that's been stained with a particular dye. And this is a three-dimensional culture. And traditionally, we've always grown cancer cells looking for drugs as in 2D. So they're kind of glued to the bottom of a well. And now we're growing these in 3D and they're much more tumor-like. So if you look at on the panel to the right there at the top, there's something that looks a little like outer space or a nebula or something. That is actually where we've taken one of our compounds that we discovered using this assay. And we can see that what it does is where you see the yellow color, it's inducing apoptosis or programmed cell death, which is how you want to kill cancer cells. It's a very controlled way of killing the cancer cells. And it's killing most of the cells. Where you see pink, those are cells that are already dead. And all of this happens within 24 to 48 hours. But what makes this really special is that when you take this same compound and you put it in the kinds of assays that we used for 30 years to find new cancer drugs, and most cancer drugs were found that way, it's totally inactive. So it's working very differently. It's actually, growing and it's just killing the cells in a different way. So we think this is a total novel way of treating cancer, and we're taking it forward into animal models and all the extensive studies you have to do to move it forward towards clinical development. So really, when you have new technologies, you can do different things and you can find totally new things. And there's really a world of new technologies to take advantage of. And with that, I'll pass it back.
Thanks, Amy. So Tom, John, let's get to some questions. Those of you who are listening, just a reminder, if you have questions, please put them into the Q&A section, and I'll be personally monitoring and bringing your questions up. Let me start with one, Tom, and this is for you. Can you elaborate on the deployments you have of your oyster and coral work?
Okay, so we're aimed at large scale deployment. So the materials we use are very economical, very easy to deploy. So there's no cranes or barges needed. And we started with a concrete based material and we've since worked to wood. So we use pine wood now. And what we found is if we take pine, which is renewable resource, and we heat treat it, that we can destroy all the natural chemical defense systems in pine, and then we add a certain nutrient, we can get oysters to grow selectively on that. Now, oysters are not really for food. This is, think of the Chesapeake Bay or New York Harbor or the southern coast of England. Equatorial Africa has a lot of oysters. That they control shoreline erosion. They filter water. One oyster can filter 50 gallons of water a day, and they're keystone species. So you can bring back whole ecosystems in a bay by having an oyster bar there. And so we're focused on a green tech solution that's economical, that you can do anywhere. Right? You can do it in a shallow water, you can do it in deep water, you can do it in a poor country.
Okay, I've got a question from Tom Guar. Hey, Tom. The specials, and Tom, this is Tom Manning, this is really for you. The spatial selectivity that you observed, 50 feet, is really incredible. Do you know why this occurs and can it be expanded?
50 feet, what is that in reference to?
The spatial selectivity you mentioned.
For oysters? Oh, for the other bacteria. Okay, so if you go to a coastline, and you pay attention to a lot of the details, for example, like when it rains, where does the fresh water go, or where do people put in boats, or how close are you to a house? That if you pick a certain or you go by depth and you start measuring things like the pH or the water salinity, or a host of other things that we look at, nitrate levels, phosphate levels, things like that, that you can move slightly down a coastline and get slightly different parameters. And so you're going to have different bacteria that might dominate in that area. Because bacteria, as I mentioned, it's an unknown area, but people throw out billions or trillions of species. So slight changes in that chemical fingerprint in a certain area can change your bacterial footprint as far as we can tell. So that's why it took a while for us to kind of figure that out. You don't put it off somebody's dock. You don't put it near a boat ramp. You have to put it in a relatively pristine area that has, the characteristics you're looking for.
Cool. Amy, I think this is for you. Can you re-explain NEC? Was that yours?
NEC.
Oh, that was
okay. I guess not.
That was you. Concrete.
Okay. This is from Elizabeth Haley. So re-explain that.
So nutrient-rich concrete is, if we put concrete out, sooner or later something's going to grow on it, but we found it can sometimes take years because the chemistry of the concrete on the surface is different than the ocean, and it is an equilibration there. So what we do in a lab is we add things such as, there's everything from sawdust to proteins, and there's a certain way that we add it so that we don't weaken the concrete too much. But the idea is that it releases a chemical cue that attracts oyster spat, brings it in, or coral larvae and brings it in. And then once it gets there, it's a slow release of nutrients so that we can get oysters to grow to full size, say in about a year, or corals actually grow a little bit faster also with some of the encrusting corals we've worked with. So it's basically like putting food out on a molecular level for some of the marine critters in an area where, there's very clear water, so it's very low nutrient levels, which is natural and that's fine. But if we want to grow them a little bit faster, we have to put a little bit more in there.
That's great. Bobby Lamont has a question, and I want to actually throw this to you, John, but it's really for all three of you. And it's about how do we partner research with commercialization to get it out of the lab and into the real world? And that's for everybody. John?
Sure. So this is something that I deal with every day and will continue to as we have an emerging model that we're developing, and often research ends at research, and it's often not known through other communities what valuable information is available that has the potential to actually be commercialized. So one of the trends that we're beginning to see happen, not just here in the US, but internationally, is the ability to create these wraparound services around researchers. So the researcher's the subject matter expert, and they're not going to be the expert in how you commercialize a product, or how you write a business plan, or how you raise money, or how you go through the intellectual property process or the tech transfer process, as an example. So you're seeing a increased alignment internally within the university structures that show the researcher the different steps, and then they're supported by a network that gets them to the next level. And that's going to become increasingly more important. And by doing that, it's not just in the university structure, but we're finding trends where we're bringing external community stakeholders into that process, so they're engaged to get it to the next level. And there's definitely more of a willingness to support research than ever before, because of the commercialized opportunities that exist, that have gone by in recent years. So in conclusion, it's setting up officially a business plan that have checks and balances, or steps that you must take in order to get it to the next level. But it's not up to the researcher to do it all on their own. They're supported by a choreographer, if you will, that gets them through the different levels.
So, Dr. Wright, how are you partnering with outside businesses to get commercialization?
So, so that's actually always is a hard step, is to do that. And usually we do it by going to meetings and presenting our science and trying to get people excited who are at companies, and then get it on board with those companies that have the resources. We've also worked with local kind of angel investors who have helped us to get the word out about some of the technologies. And I really like the idea that we just heard, where there's this community wrapping around the researcher, because most of us, we're not business people, and we really like to focus on the science. That's what excites us the most. And being able to have that business community help us is really important.
That's great. John, did you have some questions for Tom
I
and
do.
Amy?
Yeah, so first of all, I wish that Tom and Amy were my chemistry professors in my undergrad, because I'm sure I would have done a lot better with much more exciting subject material. But on Amy's front, I'm really curious about the challenges that are associated with commercialization of the research you're doing. And if you could maybe explain to our audience, what are the greatest challenges to commercialization of your technologies?
So really, for me, we just mentioned it a little bit. It's getting the things out there. And so most of us are funded by researchers, academic researchers. We're funded by grants that we get from the NIH, or the state of Florida has a Bankhead Coley. I have one of those grants. But they want to, when we get reviewed, they want us to have a lot of publications. And in order, when you publish, then you mess up your patenting. And I've done a lot of patenting. And so you need to be able to convince your tech transfer office that this is the next best thing to invest in. And there's all these kinds of challenges like that. And usually our stuff is very early stage at the beginning, and eventually, you know, it progresses towards going into clinical trials. We've had a few things go to clinical trials, and one that we worked on that succeeded, but it's a long, hard road. And that's, for me, the challenge is just, you know, finding that partnership to help us move it forward.
Great. And I do have another question too for Tom. And if I'm curious if you're able to assign a cost to Biostatin 1 made by your technique, and why do you consider it to be a green technology?
Well, the EPA has their principles of green technology, and we try to stick with them. First, I mean, it's a good teaching tool for the students to think of a chemical process like that. The second part is when we go to a private company, if we have something that's very exotic, very expensive, and can pollute like heck, they're not going to look at it. We know that it has to be cheap, easy to deploy, easy to work with, and that if they go to a county or a state or the Army Corps of Engineers with something we're working on, that they have to be able to sell it too. So the green tech part, that we're leaving no footprint, that we're using renewable resources, that we're working with stuff that people can pick with and handle and not have to worry about any kind of, poisoning or toxicity. That's something that when we go into the process, we're thinking about. So it's not at the end we say, well, how do we make this a green tech thing now? It's from the very beginning, we're starting with that mindset.
Thank you.
That's fantastic. Ann Carpenter has a question that was leading to a question I've got. How can we commercialize solutions that don't require researchers to have to do it on their own and expose their patents or whatever?
I guess that's for anybody.
Yeah, I think you'd be best.
Okay. So publisher patent. And here's the challenge. I have been a faculty member, and I know the pressure that a faculty member or researcher has in terms of instruction and service and research and hitting certain metrics, which often can distract from the core research. So there's this pressure of faculty and research-based institutions to be able to perform in different sectors, and you essentially weigh that out by a percentage. Here's where I'm spending my energy, which then can be a distraction to the core area of where the faculty member or researcher needs to focus on. So you have that published pressure as an example. On the patent side too, there are expectations within certain institutions that you are achieving remarkable successes, but you're not necessarily set up with the infrastructure or the roadmap to be able to do that. So it really is an open-ended question, and it really depends on the type of environment that you're in and the kind of role that you're expected to serve. But I've worked in public and private institutions, colleges and universities, big and small, and they all have the same common themes, but some differentiators along the way. But one thing I can tell you in my current role and in previous roles, we have to do a much better job of setting up the infrastructure that allows these patents to go beyond just the submission of a patent. And often these tech transfer or IP units within institutions don't see the value or don't have the support mechanisms, or perhaps are lacking the resources to get it to the next level. And again, this is where that public-private investment partnership opportunity comes in, because we need external stakeholders. The university shouldn't do it on its own. The subject matter expert shouldn't have to do it on their own. And that's when I go back to what I was saying earlier about thinking more business-like and entrepreneurial and innovative than ever before. You treat your research like a business, and your wraparound services and infrastructure also must treat it like a business. But it's a whole change in the mindset, which is very difficult often in academic environments.
Jane Cohen has a question. I'll throw it at you, John, but Tom and Amy jump in. What can we do to encourage public investment by legislatures so that they can get into public higher education innovation-based, so they won't have to assume that a model of self-sufficiency, self-sustainability shucks off a need for a continuing public investment?
So this is a great question, and honestly, I don't think that there's a black and white answer to it. And I also think that just in the United States, when you look at public institutions within each of the states, they have different models and they have similar models. I can speak, having worked at public institutions in different states, I can tell you what some of the challenges are. That the moment that you ask the state to help fund something, the common answer is, oh, we don't have enough resources, or we'll fund things that boost enrollment opportunities or meet different metrics. And quite honestly, the resources are often earmarked for the wrong opportunities, or there's not enough resources given to the right opportunities. So if you're working at a public institution, usually it's about enrollment at the end of the day. And then if you're research-based, okay, it's about research. So I think that we have to do a better job lobbying our governments locally and regionally, statewide, federally, to explain why we have to earmark funding that allows opportunities to become commercialized and scalable and sustainable. And often there is a huge disconnect between the legislators and the practitioners. And the practitioners are there for long term, and the legislators are short term in terms of their thinking. So we need to think much longer term and then be able to pass that on throughout the system.
So a related question for any of you from Scott Van Buskirk: how can government agencies like NOAA, for example, be more help in your areas?
I'll point out that I do, like we've all our cancer drugs have gone through National Cancer Institute for preclinical work. And we dealt a lot with NIH for antibiotics. We've gotten, we had 2 SBIRs from NOAA. So I think in a lot of ways, their resources have helped. But the thing that I've often found the best is a lot of times that the scientists, like with NOAA, you know, we're doing, say, coral restoration in Florida Keys. I can sit down and have an hour-long discussion with someone, and they can save me 6 months of research. Right? Just because they have a lot of local knowledge, they knew who the players are, they know who to stay away from. And so a lot of times just opening dialogue with people. It's the same thing with private companies, with administrators, is having kind of a positive dialogue where I'm not just asking for something, but I'm trying to learn from them, interact with them, that can really, in the long run, help you quite a bit.
We're just about to the end of our time. Amy, you go ahead.
Well, I was just going to say that also, I've seen that we have our Cooperative Institute for Ocean Exploration Research and Technology from NOAA here at Harbor Branch, and they've been great advocates and have also helped us gain funding through NIH to take things forward. So they you know, interagency advocacy has been very important as well. So there could always be more, though.
Millie, I'm going to throw back to you. And then if anybody wants to stay on afterwards, we can join in and just talk a little bit more. And sometimes we have some high-tech questions or some questions that we want to follow. So Millie, back to you.
Great, thank you. That was very interesting. So you see that there are solutions that come from the ocean that deal with great human health or with coastline resiliency that don't necessarily come from an oceanography institute, although at Harbor Branch it sure does. But at Valdosta, it's the chemistry department, a rather unexpected place, I would say, Dr. Manning. So thank you all. Dane, thank you. Dane is great. You see what Dane does when he's not helping us at Ocean Exchange. He does leadership development, and he's, I'm sure, very fabulous at it. He's in Wimberley, Texas. Someone asked that earlier. Next slide.
Right.
What's next? November 18th, same time, same place. We have an emission sniffing drone. Explicit Emission was a finalist at Ocean Exchange back, I don't know, maybe 5 years ago. They're from Denmark, and they're doing great work in the EU. They've had some connections in the US as well. Sulfur emission sniffing has been important, but some of their work is shifting, and I think you'll be very interested to hear about what those shifts are. We will also have an industry expert at that time. You can follow us at oceanexchange.org. We're on Twitter, we're on LinkedIn. We have a monthly newsletter that we encourage you to subscribe to. Thank you very much. So we'll hang on and we'll take some more questions if we have any.
Yep, we do. And Tom, you just grabbed one, I think. So why don't you take this question?
What's the question?
Oh, I'm sorry. It says, where have you done your oyster restoration?
Oh, that one. Okay. We've done it along the Atlantic coast, particularly off the coast of Georgia, and we did a lot of it in the Florida Panhandle, Apalachicola Bay and Appalachia Bay, where oysters are a big deal. I mean, the Apalachicola Bay oysters have been to the Supreme Court, and so there's a lot of, you know, that's in the layman's newspapers quite a bit.
So I've got a question for you, John. I'm going to turn it around. So, you know, we talk about what the researchers need and how to get their work funded, and I want to turn it around to the world of entrepreneurs and people who would be looking for something really useful that they could plug into a business. How does that work coming from that angle? There's so much research that's being done that people would have no idea how to find out where it is.
So it's also a really good question, and there are a lot of different answers, but there's an ecosystem that's spawning. If we just take the United States as an example, there are certain key cities that are really growing that are known as these innovative entrepreneurial hubs, and that hub system is expanding all of the time. And that's how you measure success in a community, by the number of incubators and accelerators and access to the different funding resources that are within that community. And often people will compare themselves to the Silicon Valley, say we're the Silicon Valley of the East or the South or the North, and here's all the infrastructure that they have that we want to build. And my caution there is, you'll never be Silicon Valley. You can't copy, but you can replicate certain things. But to really get down to the nature of your question, it's about creating exposure for the researcher within the community, and then the community having exposure to the researcher or to those subject matter experts that are truly coming up with great things. So one of the common things that you'll find in these innovation and entrepreneurial ecosystems now are opportunities to engage in different types of programs or events where you have have things like pitch competitions, or you have incubator or accelerator programs that works with the researcher as well as industry and potential funding sources together as a cohort or one-on-one in mentoring and coaching type environments that allows you to get to that next level. But the biggest trend that we're seeing right now is literally the blow up of these mentorship type programs that are really supporting these efforts. So there's more commercialization beginning to happen now than there ever has been in the history of research-based innovation, as an example.
That's great. Let me throw a question from Bobby Lamont, who says she's glad you're using angel investors. Does the NSF serve you in this valley of death to commercialization?
I can answer that real quick. NSF has a program called iCore, Innovation Core, and it's an expanded, like what Ocean Exchange does with the pitch. But it's a 6-week program where they take you through a commercialization process. You have to do 100 interviews, you go in front of panels, pitch your idea. It's kind of like a Shark Tank for university type thing. So it's a great experience for the students, gets them out of the classroom, out of the academic lab, meeting business people, regulations, things like that. And it's good for the faculty because you start to think a little bit different when you go through that process. So NSF does, and I think some of the other agencies have that now, iCore, Innovation Core programs. So if you're at a university, I'd really look at trying to go through one of those.
Yeah. Tom, you know what's been really fun over the last 4 or 5 years that we've had the collegiate prize going is to see one of the college teams come in and then 2 or 3 years later, see them come back as a mainstream finalist. They've commercialized the idea, or at least they're on the road to it. They've got an organization. That's been really fun. And Millie, I think I'm right that in 2019, one of those returning groups actually won one of the prizes.
That's correct. Opus 12 out of Stanford. Of course, they had already moved out of Stanford, and they went through an incubator. They were at Cyclotron Road, which is there at Berkeley Labs. They were involved in several mentoring organizations, and you can look them up, Opus 12, but they have a CO2 sequestration reuse solution. And so it's very highly technical, you know, long road to market, not easy to get there. But they went from student, won 10,000, they won 100,000 from us several years later.
That's great. Tom Guar wants to second Tom Manning's comment about iCore. He says it's a great program. Question from Jane Cohen. Do you think there's a set of local factors that could be primed to attract angel investors?
I can take that one because that's a very active conversation that I'm engaged with our community at large right now in South Florida. The challenge in attracting funding sources is that there needs to be more than just an idea. A community has to show that it has a full base of research-based institutions. It has to show that there is a talent, skills pipeline that is providing the credentials that are required to support industries and allow them to grow. And if you don't have the funding and you don't have the talent, then it makes it very difficult in order to attract money. The other issue is there's really 3 phases of money. There's love money, which comes from your rich uncle as an example that won't hesitate giving you $10,000 or $20,000, which is fairly easy to access in most cases. But then there's this venture capital money and angel investor money. And the problem is that those different audiences look at different funding amounts, which creates a valley, if you will. So it's somewhat easy to get your initial set of dollars, but then to get that second phase, which is the larger amount, is often going to be in that $500,000 or less range, and then the next level is that $2 million range. But there's a gap between that 500,000 and 2 million in many cases, and that's where a lot of researchers or entrepreneurs struggle because they can't access that. So coming up with better solutions in your community that attracts angel investors and the venture capital networks is important, but it's also important not to just focus on your local community, but how do you increase accessibility to funding sources that are outside of your community? And that's another challenge. And that's why these innovation ecosystems and the ability to communicate with each other and partner in opportunities is becoming more relevant today.
Great. Millie, did you want to jump in on that question too?
Yes, I will. So one of the things Ocean Exchange does and that we bring to the ecosystem, and all the pieces and parts bring something, but we are not particularly location based. but yet we have partners that have particular geographies. So we are part of the glue in the middle that helps bring in outsiders to a local ecosystem. And we help take local solutions and expose them to a broader audience that some of the local ecosystems can give. So that's a little Ocean Exchange commercial there, but that's our part of our mission. Yes, thanks.
Well, thanks everybody. This has been a really, really great session. It's really exciting. I mean, for you to make technical chemistry that interesting is a real accomplishment for all of you. And so thank you for doing that. And remember next month, November 18th, same time, we're going to see explicit emissions data. It's a very, very interesting technology. So bye everybody. And we'll talk to you soon.
Thank you.
Bye. Thank you.